Okay, let's get to it. So as you know, we're talking about differentiation. Right? And last time what we did was, just sort of like basic facts of differentiation, right? Like how does differentiation interact with arithmetic? How does differentiation interact with composition, right? And composition is really the nice one because composition turns into multiplication, right? You end up getting a product of derivatives. It's sort of like what you wanted to, maybe you wanted a product, the derivative of a product to turn into the product of derivatives, right? But that doesn't happen, right? Instead, you have the product rule, which is something different, right? But composition actually turns into a product, right? When you differentiate a composition, it turns into the product of the derivatives. Okay. So that's actually the right thing to think of as the analog of products. Okay, so now we're going to do as you did, back in calculus, see how how the derivative, right, controls the behavior, right, of the function. The behavior, or how it maybe controls or reflects, depending on how you think about it. Right. Okay. So, and the first thing that we're going to talk about is, things like, if you know that the derivative is always positive, then the function is going to be increasing, right? If you know that the derivative is always negative, you know the function is decreasing. If you know the derivative is always zero, you know that the function is flat. These sorts of things will, as usual, put on a more solid footing. Okay. So let's get some definitions. First off, so you have some function where x is a metric space. Right? And you have some point. You have some point in the metric space, and so if there exists a neighborhood around that point, such that the value at that point is bigger than everybody else in the neighborhood, right? Then we say f has a local maximum at P. Okay, right. I hope this is kind of an intuitive idea, right? So you have some metric space, right? And you have a function on the metric space, right? You have this point here. The point has some value, right? The function takes some value there, and you have some neighborhood. And right inside that neighborhood, this value beats all of the values, right? Then it's called a local max, right? Of course, if this were true for the entire space, then you could call it a global max, right? If this were the greatest value on all of x, then that would be a global max, right? But mainly what we're interested in is these things called local maxes, right? So like I am the local max of height, right? Everybody is sort of a local max with regards to height, because you can say, look, there's nobody, I'm the tallest person in this neighborhood here, right? So I'm a local max. Everybody is locally the tallest person. The tallest person. Okay. Okay. Oh yeah. So as usual, the first thing we're going to do is the critical point theorem, right? Which says that if you have so you have some function like this, and if f has, if 1, f has a local max at some point, x in a b, and 2, f is differentiable there, then it must be that the derivative is 0. Right? So this is something you used back, back in wherever, back in the past. And of course, one of the consequences is that, so if f has a local max somewhere, then either the derivative is 0 there, or the derivative doesn't exist. Right? So just logically, that's a consequence of this theorem, right? And so these things are called critical points, right? You know this. Okay. Okay. So okay, so like we said last time, a lot of things about the theory of differentiation can be understood by realizing that differentiable means line-like, right? Differentiable means that as you zoom in, you're basically like a line. Remember the definition, the sort of alternate viewpoint that f differentiable at x is the same thing as saying that f of t is f of x plus f prime x, t minus x, plus some function times t minus x, right? So try to make sure that this is this should be just as accessible to you as your standard definition of differentiability. Make sure that if I ask you what does it mean to be differentiable at x, and you say, well, the limit of this over this exists. This exists, right? That's sort of this is probably very ingrained in you, right? Try to make this one as equally ingrained. Okay, so it should be just as natural to you as this one. Okay, so differentiable at x means that the function is basically the tangent line plus some error, right? Plus some error. And I've left off the important part where the limit of u of t as t goes to x is 0. Okay, that's really crucial. Really crucial, right? So differentiability means that your function is basically a tangent line plus some error that vanishes as you get close to x. Okay, so yeah, so okay, so so think if your function is differentiable and it's got a local max at a point, there's only one thing that could happen, right? That the derivative must be 0 there, right? The slope must be 0 there, right? Because if your slope is non-zero, that means as you zoom in, you're basically turning into a line with positive or negative slope, and there's no way that you could have a local max there. If I say there's a local max right here, right, and the slope of my line is positive, that's impossible, right? Negative, also impossible, right? So that's how you want to think about this, right? That sort of obviously it can't be that way. Okay, so so for example, you can think of the proof in two different ways. Sort of the standard proof that you see in calculus, you say, well, look, this thing exists. So if I take the limit from the right-hand side, and I take the limit from the left-hand side, right? Those things should exist. Those things should be equal to each other, right? Right. For this thing to exist means that the left-handed limit, that's why you're all looking confused. Yeah. The left-hand limit and the right-hand limit are the same, right? Yeah, it reminds me of, I think I've mentioned the insults of Professor Conway before, right? Have I? Like, no? Oh, I never did. Okay. I had a professor in college, you know, a super genius, John Horton Conway. He's the one who created the life. This is sort of something he probably did in like an afternoon or something. But if you know the life simulation, like a cellular automata simulation, you guys don't know it. He made that, but he made all sorts of things. One student in the class was the son of Sandy Grabner, professor of math at Pomona. He's now retired, but David Grabner was in the class, and like at one point, Grabner raised his hand and was like, "Professor Conway, what happened to Frame's rule?" Like Conway had written something up and Grabner was like, "What happened to Frame's rule?" And Conway turned around, he's like kind of this big Englishman. And he turns around and he says, "Yes, what happened to Frame's rule? Aren't you an annoying little man?" At one point, he made a mistake and then realized it, and he turned around and he said, "So that's why you were all looking so stupid." Anyway, so so this limit exists, so the left limit must equal the right limit, right? And if you think about, right, if this is x, and we restrict ourselves to the neighborhood in which this is the maximum, right? Then if we're approaching from the right-hand side, let's look at the, okay, so this is like the standard thing. If this is x, and we restrict ourselves to the neighborhood in which x is max. So like say that x is the local max here, right? Right. If you restrict yourself to that limit, to that neighborhood, and consider this thing, if we're looking at the right-hand limit, well, what do you know about t minus x? Right. T is coming from the right. T minus x is going to be positive, right? So you know that this thing is positive, right? T minus x is positive, right? And f of t minus f of x. What do you know about f of t minus f of x? It's going to be negative, right? Because f of x is the maximum, right? So you're taking something smaller minus something bigger, right? So you know that this thing is going to be negative, right? So the thing on top is negative, right? So what do you know about inside this half neighborhood here? You know that this thing is always less than or equal to 0, right? And so what does that tell you? That tells you that this limit, right, the entire limit is itself less than or equal to 0, right? Because you're taking the limit of things that are less than or equal to 0, right? On the other side, right, you know that you see that this thing is going to be positive, right? This thing is going to be positive, and again, the entire limit is going to be positive, right? And so since those are equal, this one is less than or equal to 0. This one is this will be greater than or equal to 0. Sorry, got ahead of it the first time. This one is to be greater than or equal to 0, So you know it has to equal 0, right? And so that's one way of proving it. Okay. So that's sort of like what you may have seen, what could have been shown to you in calculus. I hope it was. I don't know if it was. But is it okay if I erase this? Okay. But I think a better proof, a more intuitive proof, is to think about the second way of thinking. You know, to think with the second viewpoint. So you say, well, look, right? F differentiable at x means that this sort of thing happens. Well, suppose that f prime x is positive. Okay, and we'll get a contradiction. Okay, and then, of course, if it were less than 0, we'd also get a contradiction. So this is a more complicated proof, but I think it's more intuitive. Okay, so you say, well, look, you know, suppose that you have this point here, and you know that the slope, the tangent there is positive, right? Suppose you know the tangent there is positive. Okay. So you know that your function is basically the tangent line plus some error that vanishes, right? So, right, you know that your function, so here's the tangent line, right? You know your function is basically that line plus something that vanishes, okay? So now think, well, we know that that u of t is going to go to 0, right? So, you know, this thing here that we're adding on, you know, is basically like adding on some sort of I don't know how to say it. Like if it's adding on something that's at worst linear. Okay, right? It's at worst linear here. So so what we're going to do is we'll say, well, look, if this is bigger than 0, then since the limit of u of t is 0 as t goes to x, we know that there's some neighborhood around x in which the size of u of t is smaller than, let's say, half of f prime x. Right? Right? This thing is bigger than 0, right? F prime of x is some number bigger than 0. U of t goes to 0, right? U of t goes to 0. And so we can find a neighborhood in which u of t is relatively small compared to that slope. Okay. So then in that neighborhood, if we look at f prime plus u of t, what can you say about it? I know that u of t is smaller in absolute value than half of f prime x. Okay. Now I add this guy to f prime x. Right. I consider f prime x plus u of t. What can you say about that? Anybody see what you can say about that? I have this number. Here is 1/2 f prime x. Here is negative 1/2 f prime x. The number is trapped between here and here. I add that number onto f prime x. What's the range of the sum? Where could that sum lie? And?
Is it between 1/2 f prime x and 3/2?
Exactly, right? So it's just going to be, this thing is trapped between 1/2 f prime x and 3/2 f prime x. Right? Right? Okay. So now if we look over there, so in that neighborhood, this is trapped between here. And so what does that tell you? That tells you that f of t, well, f of t, yeah, so f of t is going to be bigger than, let me write it this way. So we know that f of t equals, I'm just going to put these two terms together, right? I'm going to just distribute out the t minus x. That thing is equal to f prime x plus u of t times t minus x, right? Okay. And we know that this thing here, right, is bigger than, this thing here is bigger than 1/2 f prime x, right? So this thing here is bigger than f of x plus 1/2 f prime x t minus x. Is that okay? You guys getting that? Okay. So what does that say? That f of t, f of t, if this is the slope, then I know that my function is going to be bigger than, if I just look on the right hand side, here's my function, here's the tangent line, the slope is f prime x. If I make another line whose slope is 1/2 f prime x, I know that my function is bigger than that guy, right? My function is bigger than that guy in that neighborhood. But that means that points on the right are going to be bigger than my point in the middle, right? So, let me say it again. Here's x. Here's supposedly my maximum, my max. Here's supposedly my max. Here's my tangent line. Okay. What I know about my function is that I can make it as close to the tangent line as I desire. Okay. So what I do is I choose a neighborhood. In which I know that my function my function has to be trapped between these two lines. Okay. So I don't know exactly how my function works, but I know that I can find a place where my function is trapped inside here, right? But that tells me, in particular, that on the right-hand side, that my function is going to be bigger than my point there, right? Because the slope is positive. Did that make sense? I don't know if that made sense. I'm gonna say it a little bit differently. I don't know if this will help or not, but we should get on board. Think like this. Look. If I take f of t and I subtract off this thing here, f prime x, t of x, t minus x, then what I'm left with on the other side is f of x plus u of t, t plus x, t minus x. Okay. Now u of t is trapped between 1/2 f prime x and 3/2 f prime x. 3/2 f prime x, right? That's, we restrict it to the place where u of t is you know, I'm sorry, u of t is trapped between, between negative 1/2 f prime x and positive 1/2 f prime x, right? So actually, let me read it like this. F of t minus f of x plus this thing equals this thing on the right. Okay, so what that says is that here's your tangent line, right? We know that if we look at this thing here, right, it's trapped between something of half the slope and that thing's reflection, right? So the error here is trapped between these two things here. Okay. Okay. Now, what does that tell you? That tells you that the function, right? The function is trapped between, this thing plus that error, and the error has to be between here and here, right? The function has to be trapped in this kind of tube here, right? This narrowing tube, right? But that tells you that the function is increasing, right? That tells you that the function is increasing because the slope of this lower guy is positive. Right? Okay, I don't know if that helped. I don't know if that was any better or worse, but this is I think sort of a more intuitive way of thinking about how this behavior is, right? If the function is positive, right? If the derivative is positive somewhere, right? If the derivative is positive somewhere, then you can basically make the function really as close to that line as you desire, and that would mean that your function has to be increasing. That's a contradiction, right? Because the function this should have been the max, but actually your function is higher than this line here, right? Which means and the line is increasing, right? So your function must have some higher values there. Okay. That's maybe too much about the critical point theorem. Okay, some easier stuff. So we're going to head towards the mean value theorem now. So Rolle's theorem. In case, if you remember Rolle's theorem, it says that if you have a function on a closed and bounded interval, and f of a equals f of b, then there must be some point between a and b where the derivative is 0. Okay, right? You have some function, it has equal values at the end, and you know that there must be some point, the function is differentiable, so f continuous on AB and differentiable on the interior. You know you're guaranteed some place where the function is 0. You're guaranteed at least one point. In this picture, there's 3 points, but you have at least one point where the derivative is 0. Okay. So the proof of this, does anybody know the proof of this? So here's the hint. You have a function, continuous function on a closed and bounded interval. And so you can invoke some theorem.
It's compact.
Compact, yep. Because of the compactness, you know that the image is going to be compact. And so it's going to contain its limit points, right? Because it'll be closed, right? And because of that, it will contain its supremum, right? So the extreme value theorem, right? So by the extreme value theorem, you know that f must attain a maximum value and a minimum value at some points. At some point x in AB and at some point y in AB. Okay, so you know that it's got to attain a max somewhere and it's got to attain a min somewhere. Okay, so so we're done, sort of, right? Why would I say so we're done? Well, how does having a max ensure that the derivative will be 0? Yes, your eyes went in the right direction, right? Your eyes went to the right. Critical point theorem, right? We just said if you have a max, the derivative is defined there, then the derivative is going to be 0, right? So if x or y occurs in AB, then we're done, right? F prime must be 0. Okay. So that's, and if if neither occurs in AB, in the interior, then they are at A and B. Right? If they're not in the interior, they must be at those endpoints, right? But if they're at the endpoints, well, what does that tell you? That they are equal to each other, right? But that means that the maximum value and the minimum value are equal to each other, which means that it's flat, right? So f is constant, right? And you definitely have points where the derivative is 0. Okay, is that all right? Is that all right? Pretty straightforward. Like something that could have been shown to you in calculus. Was this shown to you in calculus? Was this proven in calculus? No. Could you have understood this in calculus? Yeah, right? Definitely. Okay, so let me give something that nobody calls, except for me, calls Rolle's theorem 2. So same sort of thing. If you have f, but now we've got two functions. Suppose you have f and g, and they're both continuous on the closed set and differentiable on the interior. Okay, so you've got these two functions. Okay, and suppose that f of a minus g of a equals f of b minus g of b. Okay, so suppose the starting and ending differences are the same. Okay, so these are equal. Okay. Okay. Then, can anybody guess what I'm going to say? it'll be in consequence, a consequence of Rolle's theorem. Rolle's theorem is basically saying if you have a car and it starts and ends at the same points, then there must be some point where it stopped. Okay. So here we've got this pair of functions, but their difference is equal at the beginning and end.
Is there a point where they're both equal, like the derivatives are both equal?
Yes, exactly. There'll be some place where they have the same speed. There must be some place where they have the same speed. So there must be some C in AB where their speeds are the same. Okay. And the proof is just, you say, well, look, consider the difference, right? The difference is equal at the endpoints, right? The difference here is equal to the difference here, right? So if I were drawing a difference function, I'd see that the difference function has the same value at the endpoints. So apply Rolle's theorem to it, right? It's the difference function is as smooth as we want it to be, right? So by Rolle's theorem, there exists a C where f prime minus g prime is 0. Okay. Okay. So if you have two cars and they start at end at the same differences, then the same difference, same distance from each other, then you know that they must have been traveling the same speed at some point. Okay. Okay, now we have the generalized mean value theorem of Cauchy. Sometimes it's called Cauchy's mean value theorem. Cauchy is the king of complex analysis. If you go into complex analysis, you see Cauchy's name everywhere. Cauchy's integral formula, Cauchy's, Cauchy-Riemann equations, Cauchy, whatever. Everything is Cauchy. Okay, so here, so you've got two functions, f and g, same sort of setup. You know that f and g are continuous on AB and differentiable on the interior. But this time, we're not going to place any constraint on the functions. So we're not saying anything about, we don't say the difference at the beginning has to be equal to the difference at the end or anything like that. Okay. We just say you've got these two functions. Okay. So you just have two functions now. Okay. In that case, there's going to be this magic point where f prime of c times g of b minus g of a equals g prime of c times f of b minus f of a. Okay, so there's this kind of peculiar looking thing. Okay. Now, if you want to think of this in terms of velocities and stuff, that you can rearrange it. So let's just pretend that nothing's 0 here. Okay. So that I can divide by things. So sometimes you place a constraint. You say g prime is never 0. Okay. In that case, I can do what I'm doing here. Okay. So rearranging. You see that what we could write this as, there's a magic C where this thing equals this thing, right? the ratio of the velocities equals the ratio of the differences. But I can make it even more sort of suggestive by adding in a nice looking 1. So this is the average velocity, right, of f, and this is the average velocity of g, right? So there exists a point where the ratio of the instantaneous velocities equals the ratio of the average velocities. Okay, so that's really what Cauchy's generalized mean value theorem is saying. Okay. I don't know if I have time to do it, but let me sort of say how to do it. Okay. So here's the proof. You multiply, so multiply g by a constant. Okay, by a constant a, so that f and alpha g satisfy Rolle's theorem 2. Right? Remember what Rolle's theorem 2 demanded. Right? Rolle's theorem 2, you wanted to have f of a minus g of a equal f of b minus g of b. Right? That's what you wanted to happen. So what we want is this thing to happen. Right? We want to find a constant alpha so that this happens. Okay. And you see what you would have to do. Well, look. How should I write it? Yeah. Okay. So I'm going to rearrange a little. F of b minus f of a. I'm going to have over here alpha g of b minus g of a. Right? Alpha is going to be this number. What alpha do I need? This alpha. Right? Just elementary, calculation shows you what alpha is needed. Okay. So that's the alpha that will work. So then you say, well, okay, by Rolle's theorem 2, Rolle's 2 says that there's going to be some point where the instantaneous velocities are the same, right? There's some point where f prime c equals alpha g prime c, right? Well, that tells you that f prime c over g prime c is alpha, right? Dun, dun, dun. Right? And so that gives it to you. Okay. Okay. So I've added on this extra thing, g prime not equal to 0, so that I could divide by these things. But without it, you just have to be a little bit more careful, and you would get this. A little bit of care will allow you to get this thing. The proof is almost the same. Okay, that's it for today. See you guys next time. So next time we will show some consequences of the generalized mean value theorem. In particular, the mean value theorem is a consequence of the generalized mean value theorem. We'll do like how the function, the derivative controls the behavior, and we'll do L'Hopital's rule and some other stuff. Okay. Thank you. Okay, you're welcome.